Bună dimineața. That's good morning in Romanian, I hope. Welcome to issue number 31 of the ZOOMTOWN experiment. For today's episode, we're going to take a look at a collision avoidance system. I'll be calling it CAS most of the time, CAS as an acronym, just to make it easier and quicker to say. So if you hear me say CAS, it means Collision Avoidance System. Now, the one thing that's important to understand about this, it is not going to be a perfect system. And I already know there's some weaknesses, and we talked about that a few episodes ago. But it is a starting point for our Zoomie to be able to avoid bumping into things. Let's take a look at some of the details, and then we'll start going into some of the code and other fun things. The sensor that we're using is a Sharp GP2Y0E03 sensor. It's a typical time-of-flight sensor, uses infrared light, and it's been working quite nicely. Its minimum range is approximately 1.6 inches or 8 centimeters. Its maximum range is 20 inches or approximately 50 centimeters. The interface we're going to use is the analog output. Now, this device also has an I2C output, but in truth it takes more time, work, and effort to read the I2C as opposed to the analog. I've got an open channel in analog, so I'm going to use it to take advantage of that speed. For the functional operation of CAS, what I'm hoping it will do is detect an object within a specified range, and that will be tweaked in probably in practical testing. I need it to decelerate to a stop, thus avoiding the collision. And then when the object is cleared out, I want it to automatically restart the motion, accelerate back up to speed, and move on. Pretty straightforward. I think incorporating it in code shouldn't be too difficult. I've already been through some testing on it, but what we're working with today will be some new code, slightly refined from what I've had in the past. This is a look at the sensor itself. This is the sensor portion, and this big piece is a connector to allow our flying leads to come out so we can connect it to the PICO. It'll fit on the front edge of our front sensor bracket, and it just wedges in there like so in this area, and that holds it nice and secure and square. Doesn't need any fasteners, etc. On the Zoomie itself, this is what it looks like at the front. Here's the flying leads. The sensor is located centrally left to right, and it is set back ever so slightly. So getting my minimum distance and calibration between the sensor and the center of the wheels, which is a major reference point for a lot of calculations. And then, of course, from the sensor to an object of a known distance away, we need to calibrate as well. Moving on to the code portion of this, we're up to Zoomie-0909A, and that'll be episode 31, I hope, unless something else pops up that's more urgent and this one will get bumped out. And of course, the source code's always available on the companion website, makingstuffwithchrisdayhut.com. Links are always in the description below. Adding this in, really not a whole lot to it because it is analog input down here where we've got our hardware that we need to configure for the PICO. We've got, right here is the CAS sensor. It's hooked up to analog to digital channel number 0. And that is for our GP2Y0E03 sensor. So that's kind of all that's really needed from there. And further down in the code is the function to handle it. So we'll go down to that. That'll be at the top of my velocity control code section. And here is the function that will handle the reading of the sensor. We're going to access a global variable, cast distance, and that will be the, we'll call it the broadcast distance. There will probably be two total distances that I will need to consider. One will be the distance from the front of the Zoomie to an object, and the other will be a distance from the front of the Zoomie to the center line of the wheels. Still haven't worked out how I want to handle the math of that, because a lot of what we do is relative to the center line of the drive wheels. We're going to read the sensor. We're going to take that data, store it in a sample value. That sample will read a value of approximately 25,000 to 45,000, at least what I'm getting on my setup. I'm sure there's going to be variations. But at a value of 45,000, that would equate to 0.8 inches. Inches in fractions, a little more than 3/4 of an inch, 13/16 of an inch, if you will. And in metric, that would be 20 millimeters. And then the maximum that I was getting practical was at 12 inches, but I think the sensor also works well up to 20, but right now I'm focusing on 12. We may expand that depending on the needs, but at 12 inches, that'd be at 305 millimeters for the value coming in from the sensor at 25,000. We're going to say Vmax equals 45,000. The minimum range will be 1.6 inches. That equates to 4 centimeters. And then our value in sample converted to inches would be 1,785 of these values equals 1 inch. There's going to be an offset that we need to account for between the sensor and to the front of the Zoomie, and there will be probably a secondary offset to get the distance to the center line, but we're going to address that as that becomes an important aspect for our collision avoidance system. Our distance is not a real complicated formula. We're going to take our Vmax minus our sample value and divide that by our value amount per inch. So we're taking the max minus this and dividing it by that. We'll add in our offset and round that to 2 decimal places of precision. And that's, we don't really need to go much higher than that. We could probably go to 0.3 decimal places or 3 decimal places, which in the inch system, 3 decimal places would be 1/1000th of an inch, or for practical information, 1/3 the thickness of a piece of paper. I don't need that level of accuracy. Plus the sensor isn't that accurate. The next thing we're going to do is, if the distance is greater than I min and the distance is less than the maximum amount of 20 inches, then we're going to say the cast distance will equal the distance. Otherwise, we're going to interpret it as a bad reading, so it'll just maintain the previous reading that it had that was good. This gets rid of some of the artifacts that'll pop up where you'll get a reflection or something like that, or a bad surface where you'll get false readings. It's not uncommon, but in truth, this sensor's been pretty darn good and reliable for not giving me flyers and so forth. So this is just a buffer, or a way to clean out some of the riffraff, if you will. Now what we'll do, we will go through, run this sample program, or this program, which I've modified slightly. I added another loop above our main deterministic loop right here. So simple little loop. We're going to run it. I will check cast, get a reading from it. I'll print that reading, and we'll sleep for 50 milliseconds and then repeat. And that way we can see how the sensor performs as I bring an object into and out of range on the Zoomie. I'm going to put the Zoomie a little bit further back. Don't need to worry about the back side of the Zoomie. The sensor is located here. This will be our blockage, our collision problem, and we're going to be checking the distance from the sensor to this block. I'm going to go ahead and we'll run the program, get it going. And right now we should be about 5.1 inches from, it's easier to read this one for my eyes. So if we go back to about here, about 5 inches. I'll move it out right about there. It should be about 10 inches. And we're 10 inches. And I'm going to go all the way over to here, and we'll come in a little bit. Well, I know what I'll do. Right here, we're getting about 16 inches, so that's pretty darn close to what the sensor is reading. And now I'm going to pull the Zoomie back a little further and see if we can get the full 20-inch range out of it. Okay, well, I got to go back a little further yet. Hopefully I don't pull any wires off of it. Okay, about the best I can get with the sensor not going into false readings is just under 20 inches. So that would be the far end of anything I would want to be looking at as far as an accurate reading. Now, for precision, I don't need, for most conditions, I really don't need perfect precision as to how close an object is. Using very rough numbers right now, I'm going to say it'll take us about an inch to decelerate. So theoretically, if I'm within an inch, I need to trigger the CAS and slow down and decelerate. But I have to take into account another object that could be moving and doing the same thing. So somewhere in the neighborhood of probably 3, 4, maybe 5 inches will be our trigger point for when we should decelerate. And we'll tweak that, of course, dynamically, or not dynamically, but in practical testing. Another thing that we're going to use this sensor for is for parking and backing in and out of driveways. In some of the previous episodes when I've shown the ZOOMTOWN layout, you may have seen this. Well, actually, if you're looking overhead, you probably saw that. But what this serves, or what the purpose of this is, in a driveway, this is the barrier that the Zoomie drives up to, sort of like the garage door of your garage. I've made it gray intentionally so that it somewhat blends in with the background. And that'll make sense further down the road here. Now, the one thing with time-of-flight sensors that I've learned over time is that they can be color sensitive and they can be texture sensitive as to how repeatable they are between different objects. One of the reasons why I've picked this silver color for the Zoomie bodies is that I kind of want this and this to have the same reflective surface, same texture, so that I can get consistent readings between a Zoomie and these barriers, because those are the two most critical objects I need to detect. Of course, the Zoomies, the other ones will be moving around, but these barriers are fixed at the end of the driveway. But this is how, when I'm backing out of the driveway, say I'm going backwards, that I can use to double check between the encoders and the distance from here to where I will be in the traffic lane. Same thing for when I make the turn to pull into the driveway from the traffic lane. I can use the sensor to measure this distance so that I know how far to pull up and make sure that that sensor distance and my encoders are in correlation with each other. giving me greater repeatability, accuracy, and better localization at the destination points. Now we're back in the code again, and we're going to look at our global variables. And right here, CAS limit. It's currently set to 4 inches. 4 inches, that's about 100 millimeters. That will be our trigger distance to force the Zoomie to stop because of a CAS-related instance. Now down here, we've already talked about this routine, which is called continuously. And this is the one that provides the measurement data and translation into useful units for our purposes. And now we're in the auto adjust velocity function, and that's kind of our workhorse of most of what goes on here. And these lines right here, let's see, right there, those lines actually make the decision of what to do regarding a collision. Now we're going to call that check, and of course this should be happening at our 5 millisecond frequency of our deterministic loop. And if the CAS distance, the measurement, is less than the CAS limit, CAS will equal 0. We're going to force a stop. Otherwise, CAS will not be triggered, so it'll stay high. Kind of inverse logic for what we're doing, but it does kind of make sense for an easy translation from the data that we're being fed. So to test this, we're going to go ahead and run the cycle, and we'll see what happens. So I am going to put our white box in about the middle here. We'll hit go, and it stopped. So now let's measure that distance. Okay, just short of 3 inches. Actually about a ½ inch shorter, about 13 millimeters short. But let's just see what it does next. And that would be the end of the movement. So the behavior is exactly what I want. I want it to start and stop automatically. Actually, let's try this old guy. Okay, that stopped. So did that. And that might be stopping up against the barrier, and there was the little final last segment of the move. Now, remember I said I wanted it to stop 4 inches away, correct? We'll go, trigger, and then coasts to a stop. So if it was triggered at 4 inches, don't want to make it mad, and we're at about 2.5 inches this time, there is going to be a decel distance. And as I remember correctly, the calculated decel distance is about 1 inch. So it's going to get up to full speed, detect something, and then it has to slow down. So the detection to full stop are definitely different values. Now the actual fine-tuning of that, I'm going to save that until we're in the actual ZOOMTOWN layout environment to really tweak a lot of these measurements, because I know this sensor is subjective to ambient light, textures, somewhat the environment per se. But over there, if I go through and fine tune it here, I know it's going to change when I get over to the ZOOMTOWN layout. But right now you see how this operates. And it's very seamless, and it was easily incorporated into our velocity control, our automatic velocity control routine. Now there's just one more line I want to point out so that this makes sense, and a few other things as we go further along. Now this next line right here is really a critical line in velocity control. It says target velocity, which is what we're always chasing, equals our set velocity, what we tell it we want to run at, times the system variable override, which is a value from 0 to 100, representing essentially 0% or 100% of what we are desiring. It's an override value, times the e-stop, which will either be 0 for on, 1 for off, or times CAS S, which is this setting here. So if I take this times CAS S, very simple math, and it's not detecting an object, we end up with a value, whatever this is, times 1 equals the same value. But if this, or this ever gets to a value of 0, my set value times any 0 makes it 0. So that's how I kind of minimize the amount of math, but it requires a little bit of inverse thinking with the logic of 0 being off, 1 being on, that sort of thing. Not a big deal there, but it can be confusing when you first look at it. So this pretty well wraps up what we're doing with the collision avoidance system. Now, as you can imagine, you can easily start seeing how we get into some turn situations or creeping up to our driveway barrier where it would detect sooner or false detect a potential collision, especially a turn where we're turning to avoid something, but it sees an object in the distance. So this is going to get really interesting much further down the road. But for right now, I think we've got a workable system that we can build upon. Now, next week, we're going to take a look at the Hall effect sensors and reading our stop signs. That will be magnets embedded in the roadway surface. And after that, we're going to be looking at a memory problem. So that would probably be around episode 32 or 33. But during this week, in one of my long drives to or from a customer, I got to thinking of another way I'm going to use these, not the time of flight sensors, but the photoreflective sensors that are on the bottom of the Zoomie. Came up with another way I can creatively use those, I think. So I'm looking forward to that episode as well. So that'll wrap up this episode. Thanks for watching, and I look forward to seeing you next week.